The last section we cover on the more applications of integrals. We go back to section 6.4, which is titled Work, which maybe sort of feels ironic. We're finally going to do some work with integration. Just kidding. Work is will be defined in the physics style here you'll see at the beginning. So we're going to begin by reminding ourselves that force equals mass times acceleration. Sir Isaac Newton came up with that equation. So usually we think of it as capital F equals m times a. Okay, well then what is work? Work equals a force times a distance. So when you apply a force over a given distance, you're said to be doing work, or the system is doing work. So you multiply the force you're applying over the distance that that it applies to. Okay, so there's our equation. Capital W equals capital F times D. Work equals force times distance. And then if you think, well, force equals mass times acceleration, then it's often helpful to think of work as mass times acceleration times distance, or work equals mad is something clever that people like to say. All right. So we're going to begin with a couple of non-calculus examples. I think it's a good idea before we get into integrals, just to get used to this idea of work and the formula. So let me keep that on the screen. We're going to calculate the work. And we use, the different types of units. We use metric, and we use the standard system, or sometimes called the English system. So let's take a look at this one. Part A, let's calculate the work to lift a 5-kilogram backpack 1.3 meters. So we're going to lift it straight up directly against gravity, a 5-kilogram backpack, 1.3 meters. That's a pretty heavy backpack, 5 kilograms. That'd be over 10 pounds, I believe. Okay, well, what kind of work is going on there? Well, we can see work equals mass times acceleration times distance. So here's what we've got. I'll just show you everything. Here it's not said, but our mass is the 5 kilograms. Our acceleration is 9.8 meters per second squared, because in metric, the 5 kilograms does not yet take gravity into consideration. So we need to multiply the 5 by 9.8 to the acceleration due to gravity. And our distance is 1.3 meters. And so you see that our mass is in kilograms, our distance is in meters, and that's going to give us our result. And you see the units there. So here work equals 63.7, and we say the units here in metric are joules, which you often see just denoted by a capital J. All right, let's try one with the standard system, or the English system. So we'll use pounds and feet. Let's calculate the work to lift a 7-pound jug 4 feet, and we're thinking we're lifting it directly against gravity, straight up into the air. Now here we don't need to think about acceleration, because pounds already takes acceleration of gravity into consideration. So it's just 7 times 4. So work will equal 28, and the units here, not very original, foot-pounds, which you often see as feet-pounds, FT-LB, foot-pounds, 28 foot-pounds of work. How many pounds over how many feet? Okay, so some good non-calculus examples to get us going. How is calculus going to come into this? Well, it's maybe simpler than you think on the outset. Let's say the force is not constant. Let's say we have a variable force, f of x. So the amount of force that is applied is changing over the distance. Well, then what we're going to do to find the work over the distance is think of multiplying a force times an infinitesimal little distance. And then we're going to add all of those little forces times those infinitesimal little distances. If we add them all up from A to B, then we get the total amount of work done over that distance. And really the distance here is the A to B. So where did we start? Where did we stop? So work is the integral from A to B, f of x dx, where f of x represents our variable force function. Okay, so where this section goes, we're going to see three very different applications of work. And I'll just warn you right now, they get progressively harder, which is a good way to do things usually. Okay, we're going to start with Hooke's law. Hooke's law is all about springs. Okay, so I'm going to start just by making a couple of drawings. So imagine that you've got some sort of a mass, okay, and it's attached to a spring, and we're going to say this is at rest. So the spring is just naturally that long, and there's this block attached to the end. We're going to say where that block is located there on the left side, we're going to call that 0. The spring is at rest. It hasn't been compressed. It hasn't been stretched. That's just the natural length of the spring. Really, that block is simply supporting the end of that spring. It's not pushing or pulling on it. As we start to say pull that block, then it stretches the spring, right? So actually in this system, really the only point behind the block is to give us something to grab, so we can either pull the spring or we could do the opposite, right? We could push it. So let's say we stretch that spring X units. Okay, so it's gone from at rest, it was at 0, and we started to stretch it out until we get to X. So it's stretched, or this would work the same way if we compressed X units. Now we don't want to go through the wall, I guess, but okay, you get the idea. So it turns out Hooke realized that there's a very simple function that will describe the amount of force that you need to stretch or compress a spring X units. Turns out all it is some constant times X. So here the variable force f of x is k times x. And what is k? Well, we call it the spring constant. Really the idea behind k, it's a number that it's basically, it describes like the ruggedness, if you will, of that spring. How loose or kind of weak is that spring, or how rough and rugged is that spring? Does it stretch easily, or is it very difficult to stretch or compress? So the more difficult the spring is, the higher the value of k. And it turns out you multiply your distance by k, that's how much force it takes. And it makes sense, right? So, if I stretch the spring, a little bit, that doesn't maybe take much force, but the more I stretch that spring, the harder it gets to stretch it, that much further. So maybe like the first couple of inches is easy, but then the next couple of inches, right, the same distance is going to be a lot more difficult than the first few. And that would be represented by this simple formula here. Okay, let's check out some examples. Here we go. Let's say a force of 25 newtons is required to stretch a spring 0.1 meters. So you can tell we are using metric here. We've got forces in newtons. Our spring is being stretched in meters. Okay, so we know how many newtons it takes to stretch it, 0.1 meters. So part A says, how much work will it take to stretch it 0.4 meters? So we know how much to stretch it 0.1. How much work to stretch it 0.4 from its resting length, if you will? We say, okay, well, yeah, let's think about this. And you can see I'm going to have kind of work on both sides. Let me cover up what's going on that right side here, so I don't give too much away. So we're going to start with f of x equals k times x, and our first job is to figure out the k that will go with this particular spring. And so that information they give us at the beginning, the 25 newtons will stretch at 0.1, that's going to be enough to figure out the value of k for this system. So how is that? Well, the force is 25 newtons, and it stretched at 0.1, so that's x. So we can plug in 25 for F, 0.1 for x, and we'll be able to easily figure out the value of k for this particular spring. It's 250. Well, that's a pretty high value of k, and it's the first example we've seen, but 250, oh man, this must be a pretty tough spring. All right. So what does that mean? We can plug that k back into our variable force function. Here, f of x would equal 250x. Okay. So we can go for our integral at this point if we know f of x and we know how far we want to stretch our spring. We're going to say the work will be the integral from 0 at rest to stretching at 0.4, 0 to 0.4, f of x, 250x dx. And that doesn't sound too bad, right? We can integrate that. We don't need any special techniques here. 125x squared from 0 to 0.4, and I'll just tell you the final answer. Plugging in that 0.4 would give you 20, and obviously plugging in the 0 would be 0. So your answer here, the work equals 20, and the units are joules with a capital J. One thing just to keep in mind as you're doing these, your units need to be newtons and meters. So when you're working, if you've got newtons, it's got to be newtons and it's got to be meters. Sometimes you might see in the homework they might throw you like centimeters. It stretches at 10 centimeters. Well, it's, in order for the units to match up, it's got to be in meters. So just something to watch out for in the homework. Another thing I should probably point out at this point, now that we've seen an integral, keep in mind this is section 6.4 in the book. It's just the way our author decided to arrange things. So what does that mean for us? Well, this is before anything in chapter 7. So all of the integrals you're going to see here in 6.4 are just going to be integrals, Calc 1 style integrals. So, polynomials, maybe you'll get a u sub, maybe, but they tend to be much simpler. The difficult part about this section is just setting the integrals up in the first place. We're going to see more of that soon enough. Okay, I've also got a part B to this question. And it goes, how much work to stretch it from 0.4 to 0.6 meters? So let's say we've already stretched it 0.4 meters. And so that work has already been done. That 20 joules is already accomplished. And now we want to go a little bit further from 0.4 to 0.6. How much work, how many joules to get that last 0.2 meters? Let's find out. Well, we've already got f of x equals 250x. So we've already figured out the k, right? So all we got to do is set up the integral. Work will equal the integral from 0.4 to 0.6. 250x dx, and well, we're going to have this answer pretty fast. 125x squared from 0.4 to 0.6. Plug those numbers in, and I'm just going to tell you the final answer here. Let's just get to it. Turns out the work is 25 joules to go from 0.4 to 0.6, which maybe is surprising, maybe not, right? So only 20 joules to go from 0 to 0.4, but to go from 0.4 to 0.6, right? only half the distance, but it's that extra bit. That's another 25 joules. So it's definitely getting more difficult to stretch this spring as it gets further away from its happy place, from it being at rest. Okay, that is what we've got for Hooke's law. Um, more applications coming up.